Hello everyone, my name is Jun Tang from School of Mathematics and Information Technology, Yuncheng University. The title of my presentation is the Electron Landau level stability coefficients and applied to the electron Fermi energy and electron pressure in super high magnetic field. Please let me introduce the research background briefly. Magnetars are a kind of plus powered by their magnetic energy rather than their relation energy. They are categorized into two populations: historic soft gamma X-ray repeaters and anomalous X-rays. Plus, for the complete degenerate and reactive electrons in beta and equilibrium, the distribution function obeys Fermi-Dirac statistic. When the temperature approaches zero, the electrochemical potential mu is also called electron Fermi energy. Many authors have carried out studies on the influence of a super high magnetic field on the compositions and equations of state of a neutron star. In the previous work, Professor Gao and his colleagues discussed the quantization of the electron Landau levels and explored that the influence of quantum electrodynamic effects on the EOS. In this work, we investigate the electron Landau level stability and its influence and electron Fermi energy. The electron pressure in the circumstance of magnets by introducing the Dirac delta function, we deduce general expressions of EFE and PE and obtain their particular solutions in super high magnetic fields. Compared with our previous work, this solution have a lower magnetic field index of beta equals 1.6. By modifying the free space of relativistic electrons, a super high magnetic field can enhance the electron number times Ne and decrease the maximum of electron Landau level number, which results in a distribution of the electrons. The results are expected to facilitate the study of the weak interaction process inside neutron stars and the magnetic thermal evolution mechanism for magnetars. Second, our main question includes: first, how a super high magnetic field influence Landau level of relative electrons and their Fermi energy and pressure. Second, a popular view is that in a super high magnetic field, the higher the magnetic field intensity, the lower electron female energy and electron pressure. How to charge it? In pressure work, Professor Gao and his colleagues investigated the quantization of the electron Landau levels and explored the influence of quantum electrodynamics effects on the EOS. The main conclusions include the higher the magnetic field intensity, the bigger the electron pressure, and the high pressure is caused by high Fermi energy of electrons. The total pressure of a magnetar is always asymptotic compared with ordinary radio pulse. A magnetar source might be a density Ns if the asymptotic pressure is taken into conditional rate. Their research results pose a challenge to the prevalent viewpoint. In a super high magnetic field, the higher the magnetic field intensity, the lower the electron female energy and the electron pressure. This prevents the viewpoint essentially goes against the really equivalent of the quantization of Landau level due to the introduction of an artificial and false assumption and the application of the solution of a non-realistic electron cyclotron motion equation. The third equation is that with the increase in the magnetic field intensity, how the Landau cylinder become and how about the stability of electron Landau levels. Last question: how to derive a special solution to electron female energy, as well as a special solution to electron pressure? What are their significance in the astronomy and astrophysics? Our method includes 1. The maximum Landau level number of electrons is set by the condition that the maximum electron female Fermi momentum is larger than 0. 2. Introduce the Landau level stability coefficient of electrons Gn in a SMF and assume that it takes the Pauli law form. 3. We introduce the Dirac data function for electrons in a SMF and the electron momentum perpendicular. 4. According to the requirement of the Pauli exclusion, principle. The electron energy state density equals the electron number density. 5. By comparing electron, Fermi energy is SMF, and that without SMF, we determine the stability index of Landau level. We applying a special solution of electron Fermi energy EFE and electron pressure PE in SMF, and make plots of the EFE versus B and PE versus B. Both of these two quantities increase with the magnetic field strength. We expect our results to explain the magnetars activities, especially soft X or gamma ray emission and explain the super Kalinskar mass, white drives, and slowing the EOS of higher magnetized white drives. That's all. Thank you.